The Large Hadron Collider is a machine which collides protons and a very high energy. Now with the run 2, we are going to reach an energy level twice as big as the previous run, which gave us the Higgs boson.
Scientists on the 4 major Large Hadron Collider experiments, ATLAS, CMS, ELISE, and LHCb, are colliding protons and collecting data at a record-breaking energy, 13 trillion electron volts, or TeV. Claudia Frujuele, a theoretical physicist, describes what happens when protons collide in the LHC.
It's important to think about them not as protons, but in terms of the constituents of a proton. And indeed, the proton is made of a bunch of particles, and those are called quarks and gluons. So really, we have to imagine a collision between this bunch of particles.
Maybe I should have warned you. It can be a little bit of a messy subject.
Most of these particles and most of these events are known physics. So what we really are doing is like looking for rare events. We are looking for the needle in the haystack.
Something like 100 particles or more can come out of a collision, and we want to understand the trajectory of all of those particles, where each particle went, and we want to know how much energy each particle had. But when we do that, we can reconstruct what happened in the collision, and in doing so, we can learn something about our theories of how physics works on the lowest level.
That's Jim Hirschauer, and what he's talking about is potentially 100 particles resulting from a single proton collision. This isn't magic, but happens because the energy generated by a collision is converted into a slew of new particles, including electrons and photons, and less familiar particles like muons.
So the protons collide right in the center of our detector.
He's talking about the compact muon solenoid, or CMS. At Fermilab, US researchers like Jim are studying data recorded in the CMS detectors.
The detector is pretty much a big barrel, about 5 stories tall. It weighs about 14,000 tons. Different parts of the detector measure the trajectory of the particles, and other parts of the detector measure the energy of the particles produced. It's arranged in a number of layers, and I guess you could think of the layers as roughly 3 groups. There's the tracker in the very center of the barrel, and just outside that are the calorimeters, and just outside that is the muon system.
The trackers are made of silicon. Silicon is an element used to make computer chips. So the particles moving through the tracker are recording electronic signals not unlike the pixels in a digital camera. Particles move through this detector without being disturbed much, so it's great at observing their initial trajectory.
So by connecting the dots between the layers of the silicon, we can understand the trajectory of the particle, and from that we can measure the momentum of each particle, and we know exactly where it's going. The outer layers are more destructive, and that in order to measure the energy of the particles, they need to stop the movement of the particle. So after the particles go through the tracker, they will strike the calorimeter.
By slowing down particles and absorbing their energy, calorimeters help physicists observe how different particles interact with matter. Some particles are quickly absorbed, while others penetrate further into the calorimeter. Basically, you can tell a lot about a particle by the way it treats matter, and physicists look for key patterns that give away a particle's identity and its origin.
As a particle, like an electron, strikes the calorimeter, it starts within the calorimeter a little shower of more particles, which we call an electromagnetic shower. As those particles go through the crystal of the calorimeter, they produce light, and they produce light, an amount of light in proportion to the energy of the incoming electron. And so by calibrating the detector, we can understand that a certain amount of light that we get out of the calorimeter corresponds to a certain energy of the particle that struck the calorimeter in the first place.
At this point, the CMS detector has absorbed most of the particles that have come out of the collision. But there's one final layer, the muon system.
The muon particle is just like an electron, except heavier. And we know that if we see some dots to connect in the muon system, it must have been a muon because nothing else will make it through that far.
But of course, particles darting through the tracker, calorimeters, and muon system are moving way too fast for scientists to watch in real time.
The proton collisions are occurring in our detector about 40 million times a second. And that's too much data for us to record all of the information from all of the sub-detectors for every event. So we need to decide which ones are the most interesting, which collisions are the most interesting. And we do this with a trigger system. And the trigger decides very quickly, in a few microseconds, which events to record and which events to ignore. And so at the end, we might be collecting a few hundred hertz, so a few hundred collisions per second will come out of our detector, out of the 40 million collisions per second that we know is occurring in the LHC.
But even with the trigger, a few hundred collisions per second is a tremendous amount of data. During Run 1, the CMS detector produced about 5 petabytes of data per year, roughly equivalent to the data used to stream 2 million HD movies. And that's just CMS. The Atlas, ELISE, and LHCb detectors are also packing in data.
The data from those events are written to computer disks, and then eventually they are sent all over the world for analysis.
In the first run of the LHC, we discovered the Higgs boson, so now we hope to discover a new massive particle. This can be maybe dark matter. We can discover a new symmetry, like supersymmetry, and so a bunch of new objects. Or maybe we will discover something that we didn't think about.